Coming for the afternoon session. So our next speaker is John MacLennan from Cambridge Earth Sciences. Over to you.
Okay, thanks for inviting me to give this talk. I'm going to follow on a little bit from what Dan talked about this morning in terms of trying to look at some of the observations that we can use to understand melt transport in the mantle. And particularly I'm going to be looking at a little bit about uranium series disequilibria, which Dan talked about a little bit this morning. And then I'm going to look at the relationship between deglaciation and volcanism in Iceland and loading and mid-ocean ridges, and try and see if information that we can derive, observational information that we can derive from those settings, can help us to constrain the rates of melt transport and eventually to help us understand what the mode of melt transport is in the mantle. Now, observations, of course, aren't always perfect. Here's a nice satellite image of the recent Hollerøyen eruption in northern Iceland, northern central Iceland. You can see here's an ice sheet here. It's the Vatnajökull glacier, and here's the sort of active volcanic region, the northern volcanic zone. Quite a lot of the observations that I'll be referring to are from Iceland. Some of them will be from mid-ocean ridge system as well. Yeah, so observations, aren't perfect. This photograph was taken by Ewan Much, who's in the audience, out of a plane window. You can see there's something going on here. There is definitely some melt transport occurring, but we've got a sort of imperfect view of the situation for various confounding features. And that's a little bit like the situation that we're dealt with when we look at geochemical data to try and understand physical processes, or even when we do something as simple as look at the volumetric response of magmatism to changes in loading. So we're trying to interpret imperfect observations. In terms of global scope, I'll be fixing most of the discussion on the mid-ocean ridge system here, and most of it centred on Iceland itself. Now, one of the reasons why the mid-ocean ridge system is an intelligent place to start to try to understand problems of melt transport is it's a setting where we think we understand how the melt is generated fairly well. This is an overly simple view of exactly what's going on here. The plates separate, the mantle rises and undergoes adiabatic decompression melting. Melt is generated in a roughly triangular region. Somehow it's focused towards the ridge axis, where the bulk of it crystallizes at low pressures near the surface, and sometimes eruptions occur, and we can sample that material at the surface after a lot of processing. This is a very simple model here, but it means that it's just to demonstrate that we have a good understanding of how melting should occur in this tectonic setting, which I think is not entirely, this is not true in subduction zones certainly, and it's more complicated in ocean island settings as well. So this is why mid-ocean ridges are a good place to look at this problem. Now, the other advantage that we have from the mid-ocean ridge system is that in certain places globally, slices of the oceanic crust, which is one of the end products of magmatism at mid-ocean ridges, is that oceanic crust can be emplaced onto the continents during continental collision or events like that. So what that means is that we're able to, as geologists, go and actually have a look at or get a feeling for what the rock types are that are present within the oceanic crust, and build up an idea of a sort of unifying stratigraphy. And these bodies of oceanic crust that are now emplaced onto the continents we can go and look at are called ophiolites. And there's a great number of ophiolites that have been studied in huge geological detail. There's a fairly large amount known about the petrology, the petrography, the geochemistry of these. And while the structure varies from place to place, there's a sort of a typical model of what the oceanic crust and uppermost mantle looks like. We always have this structure of sediments, pillow lavas, dikes, gabbros, and plutonic rocks at depth. And then beneath this, there's almost always this ultramafic tectonite. It's a mantle rock. It's Harzbergite, and it almost always contains olivine and orthopyroxene. We know that also if you look at so here are mantle xenoliths brought up in the San Carlos event. You can see here these mantle xenoliths, these blocks of rocks, they also almost always contain olivine and orthopyroxene in them. So one of the very first constraints that we should consider when we're thinking about how melt transport works in the mantle is something that was picked out many times, but in the sort of review paper from Peter Kellerman in the late 90s, demonstrated that mid-ocean ridge basalt sits on this phase diagram. The composition of mid-ocean ridge basalt sits in here, whereas at low pressures the compositions of liquids that are in equilibrium with olivine and orthopyroxene are here somewhere. So if mid-ocean ridge basalts were in equilibrium with the shallow mantle, they'd be in equilibrium with olivine and orthopyroxene, so their composition should lie along here, but they clearly don't. And what that tells us immediately is that there's disequilibrium between mid-ocean ridge basalts and the shallowest bit of the mantle. What that means is that something like fractional melting is occurring. The melt is able to separate from the solid and make its way to the surface without complete re-equilibration with the shallow mantle that it's travelled through to get to the point of eruption. So this has got a sort of first order petrological control on the system. There's some more classic observations that tell us that mantle melting is something like a fractional process. It's the melt separates very efficiently from the solid residue after generation. I'll not go into too much detail on these just now, but this shows the composition of clinopyroxene crystals in abyssal peridotites. These are lumps of mantle rock that have been exposed at the seafloor for tectonic reasons, usually at slow spreading mid-ocean ridges. And if you measure the trace element composition of clinopyroxenes, it fits in a sort of grey shaded field in here. There's a big range in clinopyroxene compositions. If you had perfect equilibrium melting, then you'd only expect to find one clinopyroxene composition, and you wouldn't exposed in the abyssal peridotites, and you wouldn't find a huge scatter that's observed, and you certainly couldn't produce these very depleted compositions that are observed in the system. So this diversity, the presence of very low incompatible element concentrations, these light rare earth elements, in some of these clinopyroxene crystals has been taken as evidence for the importance of fractional melting, and we also see this reflected in the composition of melt inclusions, as Dan said earlier this morning. There's huge diversity. These are observations from Sobolev from the early 90s. All the lines here show the compositions of individual olivine-hosted melt inclusions. You can see some of them are very depleted. So this one here has got very depleted, very low concentrations of the light rare earth elements. In order to get a melt this depleted in the system, if you start off melting a homogeneous, typical upper mantle composition, this has to be produced as the last gasp of fractional melt. Not quite, but it's something you produce after a large extent of fractional melting of the mantle. And the fact you have this diversity there just mirrors what we see in the clinopyroxenes. A final argument in favour of something like fractional melting is the fact that we observe this uranium series disequilibrium. I'll talk a little bit more about that in a few slides' time. But what this is basically, because thorium and uranium are out of equilibrium, 230 thorium and 238 uranium haven't got equal activities, this means that the thorium-uranium ratio has recently been fractionated by some process, and it's only possible to do that at extremely small melt fractions, at extremely small porosities, and that means that in order to preserve this, the melt has to be able to separate from its source regions at low porosities. Now we know there are a large number of MORB samples available from the global mid-ocean ridge system. It's becoming increasingly well sampled. This is a plot from Ollie Shortall, giving us a feeling for sample density per kilometres. You can see some parts of the mid-ocean ridge system, Juan de Fuca, East Pacific Rise, parts of the mid-Atlantic ridge, and round Iceland have got very high sampling densities now. We need to find more segments of mid-ocean ridge where we can carry out these very high density studies. But of course, the problem is that it's all good and well to have samples, but what we really need are samples with excellent sort of geological context. If you want to look at uranium series disequilibrium, you need to find samples that are young enough to retain the equilibrium, i.e. the age of eruption of the samples was young enough to be able to retain the disequilibrium. But it's actually surprisingly difficult. You know, out of this huge global data set, thousands and thousands of samples, there are very few where we have that kind of constraint. So this is just to emphasize that there are different ways of sampling the seafloor. This is dredging. You know, just throw a spiky bucket off the back of a boat, dredge it along the seafloor. It's not a very precise or it's not got great geological control when you carry out something like that. You might have some information about the bathymetry or the reflectivity of the seafloor, but it's quite difficult to be very accurate when you do this. You could try and do ocean drilling, which is expensive, but it's well worth it if you want to try and get deep into the sequence of oceanic crust, but it's not going to be able to give you, you're not going to be able to target samples that are young using this. You can also go into Alvin and try and collect samples from the seafloor. Typically, you still have very little control of the ages. You can't really do geology that easily on the seafloor. It's very, very difficult to carry this out. And you know, occasionally, so there's this famous example in 2005 when seismometers got stuck in a new lava flow on these specific rise. So in this case, you can see we have good geological control on the age of that eruption. But there are very, very few eruptions like this around the mid-ocean ridge system. So when we're dealing with timescales, it's better to be working with young samples where you have good geological control. So this is a plot which is similar, not identical to the ones that Dan showed earlier. These are just the uranium series chains, starting with over in the left. So this is coming down in atomic number from uranium all the way down to lead. And each of these isotopes, you can see here's uranium-238, thorium-230, radium-226, which are of interest here. Dan also talked about 231 protactinium and actinium-227 as part of this 235 uranium decay chain. So you can see the way it's plotted up here is each alpha decay comes vertically downwards, each beta decay steps you up to the right up here. Now, within this system, the melting process, which is ultimately what we're interested in here, or the exchange of the elements between melt and the solid mantle, that can fractionate these highly incompatible elements such as uranium, thorium, and radium. And the strength of the fractionation is dependent on a number of variables, things like the melting rate, which is going to be related to the upwelling, the solid upwelling rate of the mantle, things like the partition coefficients of the elements into the different minerals, and also the details of the mineralogy of the mantle that's melting. That's going to have a strong effect on exactly how these elements get fractionated. But we're pretty certain that the melting process can fractionate them, and then as Dan said this morning, the recovery of that initial disequilibrium back to equilibrium is controlled by the half-life of the daughter element. So this is actually from Bernard Bourdon's review paper, and he's gone for the 5 times half-life. Dan argued more for a 1 times half-life, return being the key one for estimating timescales. But what this shows us is on this log scale in years, how we can use different systems to constrain different timescales. So the ones that I'm going to be mentioning today are, we've got this thorium-uranium excess, which has got, so the return to equilibrium controlled by the half-life of the daughter. That's about 75,000 years in this case. 231 protactinium's a little bit over 30,000 years. 226 radium is more like 1,600, and then lead-210 is 20 years. Now, here are some observations from a compilation in the Kellerman review paper taken from Craig Lundstrom and Ken Sims. And what this shows is for just a handful of of mid-ocean ridge basalt samples, mostly from the East Pacific Rise and from the Juan de Fuca Ridge. This is what was available in 1997. And the first thing to notice is that disequilibrium is present both in radium. Radium is in excess over thorium, and also this thorium-230 is in excess over uranium-238. These elements have been fractionated at some position in the mantle melting column, and the melt has been able to be moved to the surface or be processed through the crustal magmatic system, erupted and sampled within 1,600 years or 75,000 years. There's a hint of a negative correlation here, but it's not completely clear exactly what that means from this sample set. There has been some more work done, actually not huge amounts, but there has been some more work done over the last 20 years or so, and this is a sort of updated version of this plot from Lynn Elkins. And this is showing again radium excess plotted against thorium excess. Some of these samples with the pink rims around them are actually, they're age constrained because we know the age of the eruption. Some of these there's certain places in the Arctic where if you can know the age of the sediment beneath a basalt flow, then it also gives you an age constraint. And what these age constraints samples are showing is still roughly, you can still see there's very strong thorium excesses, there's a radium excess, perhaps there's some general negative correlation. This downwards arrow is telling us about the decay of radium-226 being more rapid than that of thorium-230. So as samples sit in the seafloor and age, they'll go downwards and then back there to equilibrium eventually after 75,000 years or 100,000 years or so. This is just showing us the observations. What the meaning of this suggestion of a negative correlation is, I'm not going to talk about just right yet. Finally, this is lead-210, which Dan referred to earlier. So lead-210 over radium-226. And what you'll remember, of course, is that between lead-210, where's it gone? Lead-210 there, and radium-226 is that radon-222, which goes into the gas. Yep. So you can fractionate lead-210 from radium-226 by degassing, but that's not what Ken Rubin in this Nature paper tried to make an argument. Of course he's aware that radon-222 is somewhere in the middle. Of course he's aware that degassing can go on, but he tried to make the argument that this lead-210 excess was derived from was a mantle melt signature rather than something that's inherited from degassing. Personally, I think it's very likely that this is what we're seeing here is a degassing signature rather than being something that you can definitively attribute to the mantle melting process. If we look, there's been some good work done on Iceland by Jana Korneef and others, and the advantage of working in Iceland, of course, is that the geological controls are much tighter. We know the ages and volumes of eruptions. We can select samples that are going to be suitable for looking at short timescales. Now, actually, it turns out a lot of the uranium series work that's been done in Iceland has not been so much concerned with the transport timescales, but more interested in how the melting process itself controls the disequilibrium. So actually, because the generation of the disequilibrium is controlled by the melting rate and therefore the solid upwelling rate, there have been a number of workers who have tried to map out the solid upwelling rates in the plume stem under Iceland by looking at uranium series disequilibrium. So that's another thing that you can try and use it for. And what's been observed, this is the actual data from Jana Korneef's paper. We see these big protactinium excesses. We see thorium excess over uranium, like we saw in mid-ocean ridges. And we see a very complicated relationship between radium excesses and thorium excesses of various confounding features. There are no strong correlation to report, but the excesses are there. So how can we go about interpreting this uranium series data? Here's one way of looking at it. The first is that if this is obviously if this was the answer, we would need to be here. It's a very simplified model of how melt transport might work in in the mantle. The idea here is that the grey background is low porosity region. The orange pipe here is a higher porosity channel, and the arrows are just showing the direction of melt transport into this higher porosity region. This is the crustal plumbing system. I don't want you to take anything away about the scales of any of these objects here. This is just a cartoon. So we remember the presence of these different uranium series excesses. So we know there's a thorium excess, protactinium excess, radium-226 excess, and lead-210 excess. If all of these were inherited at the base of the melting region, and then were quickly, transported up this high porosity channel towards the surface, with no further re-equilibration between the upwelling melts and the surrounding low porosity mantle, then you could use these excesses to tell you something about timescales of melt extraction that are short and therefore rapid upwelling velocities. So if we discount the lead-210 excess, because that seems to be that's got something to do with degassing, then if we think that the radium-226 excess comes from close to the base of the melting region, if that's where radium and thorium were fractionated, then we get like a rate of vertical melt extraction on the order of about 50 meters a year or so. But not everybody thinks this is how it works. If there's any kind of shallow re-equilibration, as the melt travels up this high porosity conduit, if there's any sort of interaction between these melts and the lower porosity regions out here where melt is still being generated, then it's possible that the radium excess and possibly the protactinium excesses could be generated in the shallow parts of the melting region over here. The thorium excess would still have to come from deep. So this is the sort of an alternative model, which is that involves more equilibration between the upwelling melts and the shallow mantle. And in that case, all that the thorium excess would give us would be the minimum constraint on the upwelling velocities of a meter a year. So it's quite, orders of magnitude different from the constraint that we get from the radium excesses. So that's where things stand with the U series. What's useful to have is a completely different type of constraint on the melt transport rates, and that can be derived by looking at the effect of deglaciation on volcanism in Iceland. So here's Ireland. You can see that on Iceland at the present day there are small glaciers that are still present, relatively small. Here's Vatnajökull, for example, is the largest one that's around at present. And you can see here's the active northern volcanic zone, the western volcanic zone, and the eastern volcanic zone. So I'll be having a look at those regions as we walk through the talk. This is a picture taken from a plane flying somewhere over just about here, looking westwards. And what you can see is the edge of a very dirty ice sheet, because it keeps on getting covered in volcanic ash. And you can see this steep-sided mountain with the flat top. That's a mountain known as Kistefell, and that was erupted underneath the ice. When the ice just extended a little bit further out, maybe you can tell something about the thickness of the ice at the time of the eruption by the height of this tabletop with respect to the base of the eruption. So you know something about the age of that. Here's a lava shield called Trotladinga, and this sort of eruption is very large, so it's about 30 kilometers cubed or so in volume, and most of these large eruptions like that took place during the early Holocene. That's to say, just after the ice went away. Now, the ice was covering at last glacial maximum time, so about 18,000 years ago. The ice is thought to have covered almost all of Iceland, up to a thickness of about 2.5, 3 kilometers in the center of the island. So the rapid sort of collapse of that ice sheet by about 12,000 years ago produced, obviously is going to have an important unloading effect on the whole magmatic system, the crustal magmatic system and the mantle melting system under Iceland. So actually, Dan sent me off on this for my PhD quite a long time ago now. And the idea was to do some sampling in Iceland, maybe a little bit of mapping, to try and investigate exactly what the effect of unloading was on the melt generation. So people think sometimes that collecting samples in Iceland is easy. So here's, this is a typical scene from a shopping centre just in the outskirts of Reykjavik. But more generally, it's a bit like this, which is freezing fog at 1,500 metres, potential hypothermia. So, it takes some hardiness to do some of this work. But the people who've actually done a huge amount of work that enables us to make these sort of studies, of course, are the Icelandic geologists. So over the last few years, there have been a number of spectacularly good maps that have actually now come to publication, which is a fantastic thing. The data, the ideas have existed for a long time, but now the Icelandic geologists have produced these fantastically detailed maps of the extent of individual lava flows and the ages of the flows. And the way that they're able to do this is via tephrochronology. If they are able to identify a tephra layer of a given age, then they can map it out and establish whether a given lava flow is above or below that tephra layer. So that gives us pretty good time constraints on the eruptive history after the ice went away. Okay? Before the ice went away, it's much harder to constrain the time scales, the ages of eruptions, and we're left with the situation for subglacial eruptions. Pretty much all we can say is they're subglacial. But anyway, we have a great geological record of it. This is a map of southwest Iceland by Christian Simonsen. It's been published in the last couple of years. Here's one of the northern part of the northern volcanic zone by Christian as well. And this map of the western volcanic zone is actually from John Sinton's paper about 10 years ago. So there's these three parts of Iceland where we've got a very good feeling for the ages of the eruptions, the volumes of the eruptions we can estimate. And we also are able to go and sample and determine the geochemistry of the different eruptive materials. What this plot here shows is so here we are in the last glacial maximum, here we are at the present day. This grey bar shows the time of rapid deglaciation of the island. And same here. And the blue shaded areas show estimates of the sort of cumulative volume of erupted products. This is just for the northern volcanic zone, so this would be roughly for this area up in the northernmost bit of Iceland, for the last deglaciation. And what you can see is that at the time of deglaciation, there was a huge increase in eruption rates, or volcanic productivity is probably the right way to express that, in that you had about 40 kilometres cubed worth of material was erupted, so about 80% of the total volume of material that's been generated through the last glacial cycle that is still preserved came out just in this rapid burst of volcanic activity just as the ice was unloaded from this region. And you can see that as we went very quickly, the volcanic activity, so this is a sort of cumulative curve, the volcanic activity dropped back to much lower values. I've also shown the results of some model predictions, which I'll return to a little bit later. Another important point is that during this time, the data again is shown in these blue squares. There's a big change, there's a big drop, a big change in the geochemistry of the eruptions. So materials erupted during glacial times, and to a certain extent on the later part of the Holocene, so for the last 5,000 years, as this relatively what we call enriched or high lanthanum ytterbium ratios. They look like they're small degree deeper mantle melts, whereas the material that's generated associated with this burst in volcanic activity has got low lanthanum ytterbium ratios. It looks like it's made by higher degrees of melting or from shallower in the melting region from a more depleted source. But there's a distinctive and very robust change in activity. These sort of variations are, I think actually, they're best understood in the northern part of Iceland. But here's a similar sort of curve that was generated by John Sinton for southwest Iceland and for the western volcanic zone. And again, this is showing the cumulative eruptive volume and age in thousands of years before present. Here's the burst in volcanic productivity that takes place just after the ice has gone away, and then you can see it returns back to more of a steady state value as we move into the last few thousand years. So in the northern volcanic zone, where the constraints on the ages from the tephrochronology tell us that the peak volcanic productivity during this time was about 40 to 50 times higher than the productivity during more steady state activity after the burst. In the western volcanic zone, it looks like the difference is smaller, so this peak is you can see about 6 times higher on this this slope than what we find coming up to the present day. So there's some differences as we go across the island. There are reasons for that, but across what we know of the island, we have this early burst in post-glacial activity. So Matthew, Joel and Dan modelled or tried to develop a model of how you could account for this burst in volcanic activity by examining the effect of removing an ice load on the melting region underneath Iceland, which is treated as a mid-ocean ridge spreading system here. And if they predicted how you would expect, this is the melting rate to respond to removal of an ice load. This is time, so here's the ice load sitting here, be a couple of kilometres thick, and you see it's got this prescribed shape. And over 1,000 years, the ice load shrinks rapidly. And that matches what we know from the geomorphological record of the shrinking of the ice sheet. And what the results of these calculations from Matthew's thesis show us that that you have the biggest effect on decompression, there's dP over dt. The biggest effect on decompression is, of course, in the shallowest part of the mantle underneath the unloading ice sheet. And then as the unloading stops, then you return pretty rapidly to sort of steady state decompression rates. Because the melting rate is proportional to the decompression rate, this huge increase in decompression rates in the shallow mantle when you take the ice off is reflected in a big predicted increase in mantle melting rates. So everywhere in the melting region feels this increase in melting rates, but it's most keenly felt in the shallow part of the melting region. And it's possible to go through and make predictions from such models for how you'd expect the volcanic productivity to change if the volcanic productivity exactly matches up with the mantle melting productivity. And that looks something like this. And you can also predict what you'd expect for shifts in the geochemistry. So this is showing a model prediction that fits the change not too badly. Not so well at the present day, but you have the same sense of return in these model predictions. And the reason for this is this shift to these low lanthanum euterbiums in the early post-glacial burst in volcanic activity is because the melting is being biased towards the shallower parts of the melting region where we generate melts with that sort of composition. So I added into this model, I just added a finite vertical transport velocity just to see what sort of range of transport velocities could you have that would allow you to match the observations. Because we know when the ice came off, it seems fairly robust conclusion that the ice removal did affect the mantle melting. Then we know when the burst in volcanic activity took place. So clearly, if it took 10,000 years for the melt to get from the melting region to eruption, then there'd be a long time lag between deglaciation and the burst in volcanism. But the burst in volcanism and deglaciation are almost coincident, as far as we can tell. I think so. This is showing if it was 10 meters per year vertical velocity, you get a very smeared out peak in volcanic activity, and it's offset by a few thousand years. The observations look much more like we've got something that's pretty sharp, and it takes place not long after the ice went away. So it's the result there from Iceland, that the deglaciation results, is that the vertical transport velocities are something like 50 meters a year or so.
How can there not be at least a small increase
if melts are produced shallow, say at 0 depth,
Mm-hmm.
then there must be some increase, even if it's moving
Oh,
slow.
sure.
You just can't see it.
It's just small.
Okay.
Yeah. So, I mean, this all subject to relationship between loading, so ice loading, glaciation, climatic variations, and magmatism is a sort of growth industry at the moment. And there have been a number of attempts to examine how. So clearly, when you grow ice sheets globally, you're also going to vary sea level, and variation in sea level could, for as far as mid-ocean ridge melting is concerned, have an effect on how the rate of decompression melting works. So there could also be a response of the entire mid-ocean ridge system to sort of climatic forcing by changing the load of sea level. Indeed, Rich has looked at this, and Lund has looked at this. There's been a few studies, and in all of these studies, there's the chance that there's some information recorded in a possible response of the mid-ocean ridge magmatism to sea level change that might be able to tell us something about melt transport rates. There's some prospect of that. I think the observations in Iceland are extremely robust. The observations from mid-ocean ridges, they're not. I don't think they quite so robustly give us melt transport rates as yet, but it's certainly something that's worth looking at. So this is from the recent Crowley paper in Science. This is looking at spreading ridge between Australia and Antarctica. And what these authors were very impressed by was the shape of the seafloor. So variation in the bathymetry that seemed to contain, in its, if you look at the spectrum of variation of the seafloor, seemed to contain some sort of peaks at timescales that you'd expect from Milankovitch forcing of sea level, which is a very interesting result. Now, to get that to work, to get the melt generation in the mantle beneath the mid-ocean ridge to respond to sea level variation, that in a way that is then preserved in the oceanic crustal thickness and therefore the bathymetry, that contains some information about what melt transport rates might be. So the sort of peak melt transport rates, when you've got the peak admittance between the bathymetry and the sea level forcing on the melt generation, was made the estimate like a melt transport rate in the order of 1 metre a year. So much lower than what I was recovering from Iceland, more like a metre a year was the suggestion there. And Burley and Katz were looking at the response of CO2 release from the mid-ocean ridge system. So that's going to be modulated. If you change the melt production in response to changing sea level loading, that's going to eventually be reflected in a change in the magma flux, the shallow parts of the mid-ocean ridge system, which may then eventually be reflected in changing magmatic CO2 fluxes into the oceans, which is, again, a very interesting idea. And you can, in order to get that to work, of course, because in order to increase melting rates under mid-ocean ridge, you have to be decreasing the load of sea level. And you decrease the load of sea level when you're growing ice sheets elsewhere. So in order to get like a kick in CO2 production globally when we need it, which is at the end of the ice ages from the observational record, that means that there has to be quite significant delay time between ice sheet growth, gradual sea level fall, the production of melt at depth, and then the subsequent transport and CO2 release. So they went for, this is for a sort of global ensemble of mid-ocean ridges, went for, again for about 1 metre a year, sort of average melt transport rates for this to work. Even more recently, there's this paper from Lund et al. Looking at the specific rise, and this again is a very interesting idea. They were looked at hydrothermal sediments that were deposited, around vent fields on the specific ridge, and again there's a strong temporal variation. And for example, if you look at the iron flux as recorded by the sediments, and this is showing calendar. So this is going from here is old and here is young, and the grey bar here is roughly the time of deglaciation from Iceland. So it's between 20 and 8,000 years ago. This period. And what you see is there's a big spike in the iron flux recorded by the sediments. It goes up by about factor of 3 or so for quite a short period of time. And again, this was attributed to the effect of ice growth, sea level drop, unloading of the melting region, increase of more melt, slow transfer towards crustal magma chambers, increasing of the intensity of hydrothermal circulation, and then that being reflected in the hydrothermal sediments. There's certainly something impressive going on in the observations here. The implication, if you go for that sequence of events as being the cause of that increase in iron flux, then you'd again have to have melt transport rates in the order of 2 to 5 meters per year. So yeah, I think it's hard to see how you could have such a sharp increase over such a short period of time and such a high amplitude response if it's forced by the sort of slow, what's observed is the sort of slow sea level fall associated with the long and slow growth of the ice sheets, because the growth of glaciers is slow. Yeah.
Not slow. At the transition from marine isotope stage 3 to 2, there's a sudden 50-meter drop in sea level.
But is it good? So but you have to have increased the fluxes by a factor of 3 for just that amount of time. Is this completely? Can you reproduce that from? So you'd have to increase the magmatic fluxes by a factor of 3 for that amount of time.
No, those are proportional.
Okay. So these would be so from the Icelandic deglaciation, we get melt transport times about 50 meters a year. Well, not to me. Yeah, I worked on this. I feel these are quite a robust constraint. From these studies of the mid-ocean ridges, you get like slower melt transport times. So are these, is this wrong? Are these wrong? Can they all be reconciled? How should we sort of prioritize how we look at those different observations? So I tried to think about ways of making them consistent with each other. If you look at just the effect of like spreading rate, so the slowest spreading rate is the one in the Australian Antarctic ridge. Iceland's slow as well, and you compare that with the specific rise. So since the melt upwelling rate is proportional to the solid upwelling rate, some power you'd expect places with faster spreading rates should have faster solid upwelling rates and therefore faster melt motion. And that could potentially account for possible difference between the specific rise and the Australian Antarctic ridge observations, but would predict that Iceland would be slowest if that's the only thing that's changing. Another option is to think about the melt fluxes. So clearly, when we take the ice from Iceland, we increase the mantle melting rate by maybe a factor of 50. So we're going to change the flux, and as you change the flux, then depending on how exactly, so the flux is going to be related to the porosity and the upwelling velocity of the melt, depending on how these two are coupled together. So you try and couple it together through Darcy's law and this sort of permeability relationship, then you'd expect that during this deglacial burst of activity, the vertical melt velocities you'd probably expect to be higher, depending on what the value of this exponent is, by a factor of somewhere between 7 and 4. But that's not enough. So this clearly is a very, very simple first pass. It's worth like a little bit more observational scrutiny. It'd be great to see if there's some sort of numerical model that can be performed to see how we'd expect those melt transport velocities to respond to an increase in unloading, melting related to unloading. But just this simple analysis indicates that you can't account for this difference.
Sorry, phi stay for porosity? Phi.
Yes, yeah.
You've treated the Iceland as a mid-ocean ridge, but if it was just a mid-ocean ridge, it would have a crustal thickness which is a tenth of what it actually has, right?
A tenth is a bit, yeah, a third maybe. In the parts of the country, yeah. So we were looking was in the north. In the north of the country, it's 20 kilometers. So yeah,
It's a mantle plume.
Right.
There is, yes. Well, this is another discussion. So the mantle, yeah.
Your
So
upwelling rate
more.
is nothing to do with the spreading rate.
I actually don't agree for Northern Iceland for various reasons. So that in the centre of the island, the upwelling rates are likely to be much higher. If you look at the way the crustal thickness and the bathymetry change as you approach the island, it's very kind of gradual. So it looks like you're going to a place that's just getting its hotter and hotter mantle, but still just getting processed by plate separation. When you get onto the island itself, it rockets up. So basically the plume conduit, as far as I see it, is about the radius, a little bit less than the radius of the island. And that's reflected, you can see this in the strength of the uranium, so you use disequilibria as you go across, and it drops as you go towards the centre because the upwelling rates are higher. And if you look at the relation, so Infamel, for example, this rare earth element inversion breaks down entirely in the centre of Iceland because of this effect of having a plume flux in the centre. But if you go to the coast, then it works, or you can match. If you run with passive upwelling, you get match the rare earth element patterns. You get 20 kilometres of crust out. So I think the parts of Iceland that we're looking at, you can treat it. I think that the mantle flow field in the melting region is going to be dominated by the plate separation.
But what you just said was also that the temperature is vastly different. I mean,
Oh,
whether
yes,
it's upwelling or temperature, you have higher porosities at a given depth. You have deeper melting. You have
Certainly.
flux of melt.
Yes, yeah, I completely agree. Yes.
So I think the spreading rate argument is a red herring. It's not.
Yeah, well, this is temperature, melt fractions are going to be different. Melt viscosities could be different if they're hotter as well. So it would be good to know if all those numbers can be reconciled with a single physical model. That's what I'm trying to get people to do. Yeah.
Also, the importance of horizontal melt flow, right? Could be at a very different rate from vertical melt flow. And that's more important for the Meadow Ridge.
And flow down the ridge axis too. So.
Yeah.
Excess plume flow down the ridge axis.
Oh, sure. Yeah. So I believe there's there's good evidence that there's horizontal flow, solid flow down the ridge axis, and maybe even perpendicular to the ridge axis as well. But in terms of the evidence for horizontal melt flow at mantle levels is unclear, I would say, for Iceland case. In the crust, there's some evidence that there's lateral melt flow, but that's again not completely persuasive in everyone's mind. I'll just move on to just a couple of quick points that are sort of petrology related. The first is that a lot. I mean, so we can use melt transport rates to try and tell us something about what the mode of melt transport might be under ridges. Another important set of observations that I've not referred to much at all are those that have been made in the mantle section of ophiolites. So things like these dunite structures preserved in Harzbergite. And this is something that Peter Kellerman did a lot of work on in the 90s. And this has convinced a lot of people that channelization is a very important process that helps, that's important in melt transport beneath the ridge. Now, the idea behind this, as the pressure drops and the solubility of pyroxene increases in more melts, this could lead to a reaction that might look something like that. So you dissolve, the brown here is the Harzbergite, olivine and orthopyroxene. The orange colour is dunite, so olivine only. So as the melt travels up in these porous conduits, the pyroxene is dissolved and olivine is precipitated. And that sort of reaction has inspired cartoons such as this for how mantle melt transport might work under a mid-ocean ridge, this sort of downward tree of channels. But a problem has been to try and understand how the channels form. This is from one of Rich and Sam Weatherly's papers. There's a recent one coming out, and I think as time has gone on, people that are developing the models have been keener to try and get their model results to look something like this cartoon. But this, because channelization is a good way to get high melt transport velocities, and this is so there's been an ongoing debate about exactly how the channelization might occur, and I don't want to say too much about that because I was hoping like theoreticians would be able to lead us on that. But what Sam and Rich were looking at here was the effect of having more fusible heterogeneities might be entering the base of the melting region, how they might be appropriate sites to nucleate channelization. But one thing that I think is probably worth exploring is that in most of these numerical models, as far as I can understand, the phase diagram that's used, I mean, it's a good idea to keep things simple for sure. But the phase diagram that's been used is based on something like a binary phase loop with solid solution, and simplified to a pair of parallel planes. It's a good approach, and that's what's commonly been used. But what I think the channels themselves, the structures that are seen in Oman, these dunite channels with the Harsberg surrounding them, they wouldn't be generated by this sort of phase diagram. So it would be interesting if it was possible to still maintaining simple phase diagrams to look at a system where you had no solid solution. So you have like olivine and orthopyroxene, eutectics, and maybe the presence of a peritectic as well. So I think that would be an interesting thing to see what that does for the development of channels in such a system. Very quickly, I just wanted to return to Iceland and deglaciation. So this is looking at some data that Ken Sims collected a few years ago, well, a couple of years ago, on the isotopic composition of the basalts from the Thestrikar segment in northern Iceland. So Andreas Strake had done a lot of work on early post-glacial and recent flows. Ken and one of his students, Evelyn Mervyn, looked at the composition of some of the glacial samples. And the interesting thing is that what we see in the trace element geochemistry is this big shift in trace element composition just at the time of deglaciation, then a return back to something like steady state. And that change in the trace elements is also reflected in the composition of the isotopic composition. So that means that the mantle source that we're melting is slightly different as we go through this deglaciation. So here you can see here are the glacial samples, the blue triangles with these what we call relatively enriched, so high strontium 87-86 ratios. Then during early post-glacial times, this burst in volcanic activity, you shift to these more depleted values, and then towards the present day we're returning to with these red squares to more enriched values again. Now, this if the mantle was isotopically homogeneous, or if it was under this part of Iceland, then of course you wouldn't expect any isotopic variation at all. If the relationship between the fusibility of the material and isotopic composition was not strong, you wouldn't expect to see this sort of shift at all. But one way of accounting for this sort of variation is that if there are fusible heterogeneities in the mantle underneath Iceland, what would happen is that when the ice sheet is here in a sort of glacial steady state, then you would have a sort of some contribution from these fusible heterogeneities, the melts generated from them, and some contribution from a more depleted refractory surrounding mantle matrix. But as you increase the mantle melting rate during deglaciation, you increase it mostly in the shallow part of the mantle. And one way of accounting for this shift in isotopic compositions is that more of the melt is being sourced from the more depleted surrounding refractory material. And Ollie Shortall's done some work which indicates that if you look at the composition of the melts at the surface that have this enriched isotopic composition, then it looks like it's very hard to make them from melting of typical upper mantle peridotite. Maybe you could generate them by melting of something more like a garnet peroxenite, because they've got such high iron content, it's very hard to do that with typical KLB1 style peridotite. So this makes me, for Iceland at least, I like this idea that perhaps having fusible heterogeneities acting as seeds for the formation of channels might be important in focusing the melt transport, allowing us to transport melt in channels rapidly towards the surface. So I think lithological heterogeneity might be an important part in some parts of the mid-ocean ridge system. I'll just skip that. So just to summarize, so from uranium CU's disequilibrium, the melt transport rates are certainly more than a metre a year and possibly more than 50 metres a year, as long as there's no shallow re-equilibration of the melt as it's making its way towards the surface. The deglaciation of Iceland gives us a vertical melt transport velocity of about 50 meters a year. More loading effects, maybe something 1 to 5 meters a year perhaps. And these are directions, so hopefully some of the modelers in the rooms can help to reconcile these observations, try to build the effect of heterogeneity into their models, and look at the effect of simple phase diagrams. That's it.
Thank you very much, John. Questions? Dan?
Can you distinguish between blobs, which are more fusible, and a initially homogeneous material coming in, which actually melts differentially and produces the enriched material from the base of the melting zone?
Say that again. So
Well, there's two possibilities. The one that you mentioned is that your inhomogeneities are distributed through the melting zone.
Mm-hmm.
The other one is that you've got a homogeneous material which is coming in, right, but which will produce melt of a small melt fraction from the base of the melting zone,
Mm-hmm.
right, which then will actually produce the same change in the trace elements. It won't produce any isotopic changes. The isotopic things require you to do something else,
Yeah.
but the trace elements don't, I think.
That's correct, yeah. So that's why the relationship with the isotopes is important. So it looks to me like there is some relationship between the isotopic, the isotopic composition tells us that there's heterogeneity in the source regions for the trace element ratios at least, but it seems to be coupled to the fusibility of that material, and from what Ollie's done, it seems to be coupled to the major element composition of the melts that you supply to the surface. Now, the simplest answer would perhaps be that material would still all be peridotite, but it's very difficult to match the composition of the isotopically enriched materials by any experiment of peridotite melting that's happened. So that's why we're saying, garnet peroxenite melts seem to get closer.
Jerome?
But if you're going to have mantle heterogeneities, can you say something about their distribution, either compositionally or in scale, with things like composition, the variation of the ascent rate? I mean, if you've got one large blob versus many scattered, you get different chimney scales.
Yeah. So there've been attempts to define like a minimum length scale, which is based on during some melting process, you've got a length scale over which you can homogenize an isotopic signature. So the fact that we see such strong lead isotope heterogeneity in the melt inclusions, that could be, Cogiso paper would say something like 20 meters is the sort of minimum size of the heterogeneity. But unfortunately, what geochemistry I don't think can do for us is really effectively give us a maximum length scale. From the observations we've got, one half the melting region could be black, the other half of the melting region could be white, and it'd be hard to know. I think that's unlikely, but that's not a constraint that I think the isotope geochemistry can give you. So all we know is that those melts are in the plumbing system.
In the Chapter chronology, or in the isotope chemistry, or in the trace element chemistry, is there any evidence of an echo of missing melt after the deglacial pulse? There's a certain amount of melt you get out over time. You get it now, you're not going to get it later.
That's lost during glaciation. So that's melt that didn't get made during the glacial period. So it should, over the whole glacial period, it should sum to the steady state, is the idea. But the problem is, so if the model was perfect, what should happen is that when the ice gets put on, you actually should grow back the melting from the bottom up. You should see mega enriched things, but they're not found. And this is and that may be that they're there, or it may be that they were never generated. But the glacial period, we have much less geological control on. Things get eroded. There's more eruptions cover up what was there before. So could be. I like to deal with like a bit the solid geological record that we have in the Holocene, where you can more definitively use that. So, but it should average up. That deficit should be in the glacial types.
One more thing you should say, which
All right, thanks.
that the 100,000 year cycle is almost exactly matched to the upwelling. Right? And that's why you get so much at the end.
Yeah.
Rich. I mean, possibly a wild idea, but I mean, what if the deglaciation melt transport rates don't reflect melt transport under normal conditions, but it's actually a different mode? So the sudden and intense pulse of decompression leads to a different mode of melt transport. Like, you know, if you've already got these concentrated pockets of melt from heterogeneities, maybe they suddenly hydrofracture. Or
Right.
something
Yeah,
drastic.
well, because there's such a change to the melt flux, it's possible there could be you might expect a change in the style of melt transport as well. I think that's a perfectly sensible thing to say. The problem is that I see that as such a strong observation, that response, that is, the question is like whether you try and just develop models that fit the observation that you really trust, or you put it in the context of understanding that it's perhaps not entirely representative of business as usual at mid-ocean ridges or even in Iceland.
But you kind of downplayed the observation of the chemistry remaining suppressed over a longer time scale, and I wondered.
Yeah, that's like a crustal processing issue. So because most of the melts that are coming up, that are being erupted now, have got lower magnesium contents. They've spent more time in the crust being processed, so they're still feeling. There is like you can have like one characteristic residence time, but there's all sorts of melt pockets. Some of the melts from deglaciation, that trace element ratio is still going to be present in like the shallow magma chamber under Krabla that interacts with melts that have been generated at the present day, and and then it's then erupted. So you still get. That's why it's taking a longer time to kind of clean all that out of its system.
Mark? Yeah, just one. You were mentioning the missing mega-enriched stuff. There's also this basic issue, this idea of if you had the small degree melt at the bottom, as you magically get to the top. That should also have that sort of signature in trace elements. And I haven't looked recently, but have you ever seen anything like that?
No. I mean, they always look. I mean, yeah. So it always looks like a good few percent of melting. So you need like 5, 6, 7% of melting would be the minimum degree of melting of anything that you would model coming from a
Melting does nothing to the U series.
Oh, sure.
No. If you, I mean,
Yeah.
very small porosities, yes, it does.
Yeah. So it'd be small process. So yeah, there's some debate about exact. So channelization could help you to do this. So indeed, I look your paper with Peter looking at the channel, what you'd expect to come up the middle of the channels, what comes out of the low porosity regions. That actually does quite a good job for the trace elements, but it can't really account for why you have this isotopic variation that couples up with the trace elements. So we looked at the possibility that you could have these more fusible regions that got to higher melt fraction, and then once the fusible blobs get into a place where the surroundings, the matrix, the refractory matrix has got above a couple of percent or maybe less, then you can connect out, and then that gives you that.
What sort of melt fractions?
Are coming out of the fusible. Well, this is.
Because that's
we have a model that says it, but I don't trust that. I wouldn't place any weight in the numbers.
D of your.
Oh, I see. Yeah.
Bigger than D basically won't do any fractionation.
Oh.
Of uranium.
Yes, sure.
Yeah.
But you can still have. So the way this was set, and we've not modelled this, and this would be a very good thing to do. But the way the model was set up was that in the background, there's still thorium and uranium. The extent of melting at which you get the interconnection, you still have uranium and thorium in the residue in that model. But is very, very strongly dependent on exactly what you do. When do you decide to let the melts out of the fusible pod? And it just, for me, it's getting. I don't know how that relates to the observations anymore. So you can play around, but it's maybe not particularly meaningful.
Any last questions? We'll take this discussion with two. No, so there's a tea break now, and then please do come in at 4 when we will have Neil Reeby give his Rothschild lecture. We thank John once again.
Yeah,